In this lecture, I'm going to be talking about another important article about contrastive learning, but this time we use continual representation because sometimes we learn it every day we have new data is coming, and so we should adapt to the new data. So because humans have the ability to acquire, retain, and transfer knowledge over their lifespan. For intelligent agents to achieve fluent longitudinal interaction, they need to continually retain, refine, and acquire new knowledge. However, current learning approaches, in particular deep neural networks, are prone to catastrophic forgetting, a phenomenon where the network forgets its past representation as the data distribution changes. For example, for some data, we are modeling something, and then if we have new data, new distribution, then it forgets the past task. So it's different from multitask learning, and we call it continual learning, or sometimes called lifelong learning. So again, we are using this contrastive embedding just like BYOL and SimSiam architecture, but here we also need to consider the past task samples and current task samples. This representation learning module maximizes the similarity between the two augmented, because we have two augmented view of one image, or in the context of NLP we have a sentence, we have different views of that, and we create the views in NLP using, for example, dropout mask. But here in the context of computer vision, we can easily create multiple views based on different techniques, such as rotation, and the knowledge distillation module distills the knowledge, because sometimes the model is so big we need to distill the model in order to have a reduced model with much lower weights. The number of weights is reduced, and so it's more practical for embedded systems. And so let us denote as X, input as X, and labels as Y. And for incremental tasks, the output space is disjoint. The same also applies for incremental class. In the incremental domain, the output space remains the same, but the input space changes with each domain. And for each task, input label pairs are independently drawn from some task-specific distribution. The learner is tasked to learn a nonlinear mapping function using f theta encoder and g theta, which would correctly predict the output label for the input. And theta here represents the parameters of the nonlinear functions. And here the learner access to the task label, and we'll have different task learning layers per task. And this L is the loss function that need to be minimized. So we are given some data set, the network, and the encoder predictor architecture, and we have also memory buffer. So if you loop over this data set dt, that over time we get some new data, and it has only a representation learning module and knowledge distillation. We need knowledge distillation to have a better and smaller representation, because sometimes the model is big, we call it teacher model, and we have a student model, which is a distilled version of that. So everything the same, but this model is reduced, and it's good for applications such as embedded systems, and because this one has millions of weights, millions of parameters, and the other idea is that they are using this similarity loss in order to have better representation. And finally, they use this, they update the parameters. And the positive sample pairs are the embeddings of two augmented versions of the input, while the other embeddings are negative. The I and J are the positive pairs. For example, these are, we want to encourage them, we want to promote these positive pairs, and the contrastive learning objective can be defined using the info and CE loss. And Z sub I, Z sub J are the embedding of the positive sample pairs, which I have explained in that info and CE article. And we have 2n-1 negative samples. So if the number of your batch size, if the batch size grows, so you have many negative samples. As our primary objective is to learn effective and robust representations under non-stationary setting. And then we introduce the modified cosine similarity loss, which only relies on the positive samples. The task then reduces to maximizing the similarity between two augmented versions of the same input. And P1 here is the nonlinear transformation of Z1, which is proceed. So here we call this the online network. For example, in the article of BYOL or SimSium, they call it online network. And this one has stop gradient, so we call it target network. And you see the architecture is asymmetric in order to avoid that collapse to either one point or collapse to a subspace. And the representation learning module is a Siamese network, which comprised of one encoder f theta, one projection network, and a predictor network. It's like BYOL and SimSium. So inspired by BYOL and SimSium, this Siamese network has one online network and one target network. The target network provides the regression targets to train the online network, which is then used to update the gradients of the online. Because you use stop gradient, you don't use back propagation in this path. We just use a combination of weights of old and new in order to update the weights of the models. And we use the same encoder and projection network for both online and target networks. So the output P sub 1 and Z sub 2 are normalized before calculating the cosine similarity. And the loss is symmetric here because P1 and Z2, P2 and Z1, but you can also implement only this side. You have different results if you make it symmetric. And as I said, we also use knowledge distillation loss to have a better simplified and reduced model with possibly very few weights in comparison to the original teacher model. And this is the loss for distillation. And finally, we collect all these loss, and we have some hyperparameters because it's a trade-off between three different objectives: contrastive embedding, cosine similarity, and the distillation.